Umut, you can start.
Okay, I should share the screen again. Okay, great. All good?
Yes, that's visible.
Okay. Okay, yeah, so thank you for having me. So, I mean, this is a joint work with Yoel Groman, and it's part of what we've been thinking about for maybe the last 2 years, and hopefully we'll write something this summer. Yeah, it's still not written, but I thought I would tell you about this because, you know, maybe people expect me to follow up, and we are following up on what I did in my thesis and what Yoel did in his previous work. It's just taking a while. Okay, and I'm going to talk about some general framework, but I actually don't know how general this framework is. It should be more read as the most general framework that this current techniques that I'm going to explain might apply to. Okay, so M is supposed to be a geometrically bounded symplectic manifold. I will always use M for symplectic manifolds and Y for B-side objects like analytic spaces or maybe sometimes schemes too. And B is always going to be some kind of integral affine base with singularities. Okay, so now I have the M, and I also have some Lagrangian fibration. And this Lagrangian fibration, I mean, I think this Gross-Siebert type has become some kind of vague description for saying, I don't know. So it's a little vague, and I will keep it vague, but it really restricts the kind of singularities that this fibration can be allowed to have. And I won't actually spell out what kind of singularities are allowed. In general, just in 2 dimensions. And that will be later. And on top of that, I will also be making some kind of very strong large volume limit assumption. And I don't know how restrictive this is. But it's just the methods that I'm going to explain work under this assumption. And there might be other things that work under weaker assumptions. I'm not saying this is the only place where things might work. It's just the particular aspect that I will explain today. Okay, so now some kind of vague conjecture. So under this assumption, so this kind of, I have an M, and these underlying terms, I'm going to say a little bit more about those. Red underlying terms, I'm going to come back to. So under this, you know, given the data of M fibering over B, which has Gross-Siebert type singularities and has some kind of satisfies a large volume limit assumption, there should exist a lambda. So lambda is going to be the Novikov field I wrote it for arbitrary coefficients here. K could be any field, but if you want, you can think of K equals C. That fits kind of more readily to some existing constructions, but I don't think it's actually necessary. Okay, so there should exist an analytic space Y with a non-archimedean analytic torus fibration to the same base. And you know, this data should induce an integral affine structure on the smooth points of B, and it should be the same integral affine structure that I started with. And it should satisfy some kind of Stein property, which means that you can really construct this space by gluing pre-images of sets from B. Okay, so that's, maybe I want to try to explain that more. It's not Stein, but it's locally Stein, and local in terms of the base. Okay, and ideally this B would be the skeleton of this non-Archimedean space. Okay, so then somehow, so what does this mean? So it's supposed to have some consequences. So the first kind of consequence that I would want from this construction is that on the mirror, there's an invariant, global invariant that I will be interested in. And this SH sub M, I will also define what this is. but that's some kind of global invariance. And so that should be the A side. On the B side, I should be seeing some kind of de Rham cohomology. Okay, and this equality, can be true as vector spaces, as algebras, maybe slightly kind of more, somehow more imaginatively. There also on both sides, there should be spectral sequences. Check to de Rham spectral sequences with respect to certain colors. Okay, so this again, like everything, all this kind of locality can only hold, especially on the symplectic side, just on the base. Okay, so that's the main consequence of mirror symmetry that I'm going to be interested in today. But some others that I think maybe one consequence that should be particularly accessible is for every tautologically unobstructed Lagrangian, which is well behaved at infinity, this should give rise to an analytic coherent sheaf over this analytic space. And one thing that you can do with this is you can take its support and project to the base. And this should give, this should be, you can make a definition that this is the support of a Lagrangian, and it gives you information about whether this Lagrangian is displaceable from the fibers and things like that. There's already existing work about this in the case with no singularities, I think, by Ivan Smith and Nick Sheridan. There might be others. I think also, I'm forgetting his name. Danish student. How can I forget his name? Okay, maybe I will remember it later on.
And Umut, you have a question from Paul Seidel.
Okay, I'm listening.
Yeah, I'm slightly confused by this isomorphism as algebras.
Yeah.
As algebras.
SH0, I should say. So
okay.
zero degree.
Okay, all right. Okay, thank you.
Yeah, no. Yeah, I mean, there's probably a higher degree. There's higher degree versions to it. Just yeah, I didn't mean to claim. I'm gonna restrict to degree 0 right just almost now. Okay. I mean, are you saying that this cannot be true? Is that there are kind of algebra structures on both sides, right? And are you claiming that this is not possible to be an isomorphism?
I'm not claiming anything. I'm just asking, what is the algebra structure on the de Rham cohomology? Depending what it is, this means a bit different things.
Okay. That's then, yes. Then I should just restrict to degree 0. Okay. I will just restrict to degree 0. Okay, and then there could be, you can construct this coherent sheaf and look at its support. And third, of course, the one that's probably most people are interested in is homological mirror symmetry. And this is, I think there's a lot of work to be done about this. And we have some work with also Mohamed Abu Zaid that's dealing with this, but it's a long project. It will be a while until we can get to any kind of concrete homological mirror symmetry statement, I think. Okay, so today I want to focus on the special case of this closed string version, where I look at degree 0, symplectic homology on the left side, and on the B side I look at just functions. Okay. And I'm not even gonna think about algebra structures here, just like vector spaces. This is gonna be fine. Okay, so now what do I more or less mean by Gross-Seibert type? So there should be a Lagrangian section satisfying some properties. There should be a trivialization of the canonical bundle that satisfies some properties. And there should be some relationship with the integrable structure, with the Lagrangian fibration. And there should exist a limited number of local models in each dimension. I think these should be finite, and in 2 dimensions, there should be just 2 models. Well, there are just 2 models, not should be. And for this, so these models should look like on the A side, there's just a, maybe I should start using the pointer. Okay, yeah. Okay, so on the A side, I should have some kind of complete Liouville manifold with a Lagrangian fibration, such that, you know, the primitive that you have in the total space should be compatible with the fibration. So it should kind of look like an Euler type vector field in the base, kind of you know, PDQ type form. And the mirror to that is again some kind of analytic space with a fibration to the same base. But this analytic space should be kind of constructed globally. So I think it seems like it's not too unreasonable to say that it will be something like the just the spec of Viterbo type symplectic cohomology of this local model, and then you analytify this. And this B loc should have some kind of most singular point at the origin, which it's modeling. Okay, so now what is the large volume assumption? So for every point in the base of this global fibration, so now at every point I can associate to that point a model. And the model, the full model, which is a complete Liouville manifold, should have an embedding into M. I will give an example. And it should send some kind of admissible neighborhood of the local model to an admissible neighborhood of the point that I started with. So admissible here, I mean some kind of preimage of a polytope, a convex polytope. I should say convex. And just to add, just the local models themselves should satisfy this property. So the local model has the most singular point at the origin, but there are other points, and the other points should also, you know, there should be embeddings for kind of from less singular models to the non-origin points. Okay, anyway, so just, so now, so one point that I want to make is that when this happens, this embeddings, so this embedding of the local model is not unique. There are genuinely different choices of embeddings of local models, and this is related to kind of wall crossing and stuff. That's how wall crossing comes up in the way I'm going to present things. Okay, so now let me do an example. So let's start with some M, and let's say that M has a map, Lagrangian fibration over some kind of two-dimensional base. I will these will be the main spaces that I'll be dealing with later, but just for now, I think everyone has seen this picture. So there should be some kind of focus singularities of this integral of this Lagrangian fibration, and you know there's kind of monodromy around each of these nodes that we know what it is. It's some kind of shear map. Okay, let me take some kind of smooth point of this Lagrangian fibration. Okay. And now I claim that the local model for the smooth point is just T star T2 with the standard cotangent bundle form. And I claim that there should be a full embedding of T star T2 into M, which takes a polygonal neighborhood. So T star T2 has a standard Lagrangian fibration over R2. It should send a polygonal neighborhood to a polygonal neighborhood in the global object. Okay, so how one way to think about this, and there are other ways to think about it, is that you can so these cuts that I make. So these are the places you know where you kind of start with. Let's say you don't have this guy, and then you make a cut, and that the symplectic manifold changes somehow. And one way to explain how the symplectic manifold changes is as follows. So I'm just focusing on this part of my symplectic manifold, and I've drawn just the base of a Lagrangian fibration, and there's no singularities there. And the rest, anything can be happen. So this is a local operation. And what I want to do is I want to make a Symington cut inside this subset. Okay, so what I do is I choose a point here. So there are some assumptions that I'm not really spelling out, but hopefully they will be clear. So I take some kind of wedge with straight end. So it's, this is a straight line, this is a straight line. And then I take another subset inside that wedge, which is drawn with red boundary, which is strictly convex and asymptotic to the edges of the wedge. And the point of that is that if I draw a radial line from the tip of this wedge, then it should be transverse and intersected only once, this red boundary. The point is that inside this wedge, I have a Liouville structure. And this red, the preimage of this red curve in the symplectic manifold will give me a convex hypersurface with respect to that Liouville vector field. Okay, the Liouville vector field, there's no singularity, so it's just the Liouville vector field looks radial, emanating from this point. Okay, and so now, okay, so now I remove the interior of this red boundary, and then I draw a Lagrangian to the kind of, let's say that this red curve has some kind of lowest point, and I draw a straight line, Lagrangian, so a straight line from the tip of the wedge to that lowest point, and there's a Lagrangian living over it, and there's a Lagrangian at the boundary of that Lagrangian. And you can attach a Weinstein handle to that Lagrangian and obtain something with a Liouville domain with boundary and then complete. And then you should be obtaining this manifold with a cut. So
Keep going, and I have a question.
Oh, okay, so maybe I should stop for questions.
Yeah. So when you say that, so I think I understand you want to pick this red curve to have some kind of convexity property so that the Liouville flow points outwards.
Mm-hmm.
But then I want to understand when you pick this ray that meets the boundary. I mean, is there some kind of orthogonality property that you need in order to get the boundary?
The Lagrangian is invariant under the Liouville flow.
I see. Okay. Okay, I think I understand. You can arrange the Liouville flow to be basically some kind of radial.
I'm not arranging. I'm choosing that Liouville structure.
Okay.
Yes. Okay. So now, what's the outcome of this way of interpreting the Symington cut? Is that if you take the completion of this, the manifold where I remove the interior, remove this part of the red curve, then when I complete it, I just get back my original symplectic manifold. Okay, but I said that the Symington cut can be interpreted as the completion of this other Liouville manifold with the Weinstein handle attachment. But I know that the completion before the handle attachment embeds fully into the completion after the handle attachment. Okay, so this is how I get the result that I claimed, for example. So this full T star T2 should embed into this N. And there are other ways of seeing that. This happens by kind of using nodal slides. I had given another talk like a couple of weeks ago, and I have some notes from that where I had explained that there. Okay. Yeah, so, and conjecturally, if there's just one singularity, I think this is just the kind of hyperkahler rotation of the inclusion of C star squared into C2 minus a conic. So what's being missed after this embedding is a two-dimensional guy, a two-dimensional submanifold, and two-dimensional submanifold, I think, in this picture is just x equals 0 or y equals 0, depending on which coordinates you choose. And they become Lagrangian because I did this hyperkahler rotation. So that's kind of the unstable manifold. Okay. Okay, so now let me go back to kind of the general discussion. So now what I would want from this kind of this data, this Gross-Siebert type singularities plus locality, is that I should be able to find a covering of the base by some compact sets. These are generally going to be just convex polygons. And these should satisfy the following property, that if you look at SA0M for any finite intersection, so this is any finite intersection will also be a convex polygon. And if you look at its SH0, you should, so maybe one thing to add here is that normally as this homology level invariants don't come with a norm, but just SH0 for the non-negatively graded case, it does come with a natural norm. So this becomes actually a lambda Banach algebra in this case. And lambda Banach algebras can satisfy the property of being an affinoid domain. So this is a property. So yeah, I'm hoping that this general setup will tell me that this holds. And there's one more thing, which is that you should also look at the restriction maps, and the restriction maps should also give you maps of algebras that correspond to inclusions of sub-affinoid domains.
Sorry, can I make you pause? Can you, this comment about norms, it's just about, whether the image of the differential is closed or something like that?
Yes, yes.
Okay, thanks.
Yes. Okay. So then after, I could just start by making this assumption and keep going. I just wanted to say under what assumptions that we might care about that they're satisfied. So for the most of the construction, you could just start by making this assumption. But of course you want to say when they're satisfied. But I don't know if my answer was any, because I didn't actually tell you any real information. I just told you what I hoped. Okay. So now after, if this assumption holds, where I have this kind of covering with SH0 rings becoming affinoid rings, then I want to construct my analytic mirror by just gluing the Berkovits spectra of these SH0s. And this is very similar to what happens with family Fleur. I don't think that there's something very new in this procedure. Okay, but now what I want to point out is that after you have finished this construction, then something immediately follows without doing any more work, which is that this global invariant, so this statement star was the statement that the global SH, let me find this statement. So this global SH is isomorphic to entire functions in the mirror. So because of the sheaf property that this SH0 satisfy in the non-negatively graded case, which we are in, this statement that the global invariance match for just degree 0 is immediate. So as far as I understand, this is not the case for SYZ or family Fleur. For both of them, you have to kind of analyze open string invariance and kind of construct enough objects on both sides and show that the open mirror symmetry implies something about closed mirror symmetry, etc. Here you get something directly about closed mirror symmetry just by construction. And in this picture somehow, I think the one complaint that one might have is that you don't know what you got in the end. You constructed some weird space, and it's not clear why that should be helpful. So somehow I spent a lot of time lately just trying to interpret what our construction meant in 2 dimensions, and I'll try to say something. But to me, unless it means the mirror can be interpreted in some way that you can understand this, I don't see why this should be very useful, to be honest. But okay, so maybe everyone can decide that for their own. Okay, so now if you wanted to talk about higher symplectic cohomology, I do believe that it should follow from this construction that there is a higher SH corresponding to higher de Rham cohomology type result, but it requires more work. And yeah, so maybe I will just skip that comment. Okay, so any questions?
Sorry, was there, I don't know, was there a Calabi assumption at the beginning? I'm just
Yeah, yeah, there is. That's what it means to be, well, it's included in Gross-Siebert type.
Okay, thanks.
Yes.
And just, but is the Enriquez count? Does the Enriquez surface count?
No, I mean, compact surfaces just don't count in this.
Okay, but I mean, what I really mean is, are you assuming like something like 2C1 equals 0 or C1 equals 0?
So I'm assuming that there's a trivialization coming from the Lagrangian fibration structure, like in Ivan Smith's paper, for example.
You're assuming the base is orientable.
Yeah, I think
Okay.
so.
Okay, that's fine. That's what I meant. Thanks.
Okay. Okay, so now why is this kind of a strong large volume limit assumption needed? So it's because of this locality result that we could prove. And there might be other locality results. So I'm not saying that this is the only locality result. Okay, so M is again a geometrically bounded symplectic manifold. And now I want to take an open subset of M. And this open subset should be geometrically bounded itself with the restriction symplectic form. But it should satisfy more. It should also admit some dissipative Hamiltonians outside of a compact set. So I'm not going to explain what this is, but I will say that if U is a complete Liouville domain, this assumption is satisfied. Okay, so it's something to avoid holomorphic Floer solutions really looking like gradient flow lines somehow. Like that's part of it, and there's more to it than that. But so let's say it's U is just a complete Liouville domain, and it symplectically embeds into this geometrically bounded manifold. Then what we're writing now is for any compact subset that's contained in the open subset, there exists a locality isomorphism. So if you compute the symplectic cohomology of K inside U, you should get the same result. Well, there should be a canonical isomorphism between the symplectic cohomology of K inside N. Okay, and this is, so what this means is, you know, if you're interested in some compact subset that's admissible, then you find some model that whose image contains that admissible subset, and then you can say, okay, now I can make the computation inside the local model. Okay, but I want to, did I say that? Yeah, maybe I said it before. I just want to say these embeddings are not canonical. So you get, you know, you might be embedding the same symplectic manifold in different ways to M, and that will give you different locality isomorphisms. And how these locality isomorphisms relate to each other is how wall crossing happens in this framework. Okay. So now the idea to prove this is you should think of U as prescribing some very special almost complex J. So for example, in the Liouville type case, you can just think of it as a contact type J. But you want to kind of take so you can't make the almost complex structure on M equal everywhere on U to being the contact type J, but you make it more and more equal. You make it more and more equal, and as you do that, somehow it takes more and more energy for Floer solutions to leave this open subset. And then you use this kind of, the way the invariant is constructed, somehow you make this truncations. So this kind of, for every truncation level, you choose a large enough compact subset of U such that the almost complex structure looks contact type in that compact set. That's the idea, but it's a technical result that requires, and it relies on monotonicity arguments. So this is kind of Yoel's expertise. But this is the technical result that requires me to say what I'm going to say today needs this large volume limit assumption. Okay, so let me introduce a slightly more general, well, not more general, but generalize the definition of this relative symplectic cohomology to open sets. And you do this in a stupid way where you just take some kind of exhaustion of your open set, and you just take an inverse limit. of the SH relative symplectic cohomologies of this exhaustion levels. And this probably needs to be done at chain level, but we didn't really see why that's necessary yet, so we didn't do it yet. For SH0, it should be okay to just do it at the homology level. SH0 in the cases that we're interested in. Okay, so now one point is that with this definition, SHM is a symplectomorphism invariant. And for example, if you do it for the cotangent bundle of the torus, then what you get is entire functions on the analytic lambda star to the n. Okay, so if you do Viterbo symplectic cohomology, you'll get algebraic functions on the torus. But here you get analytic functions. So analytic meaning they converge on every compact set. Like they're analytic on every compact set. So the definition of entire functions also involves an inverse limit. So you have functions that converge on compact sets, and you take inverse limit of that to define this in the mirror as well. Okay, so one corollary of the locality theorem should be that if you have an open set which satisfies this dissipativity property as above, and there exists a canonical map between these symplectomorphism invariants. It's like Viterbo functoriality, but the invariants are bigger than that. They're kind of more the completed version of Viterbo symplectic cohomology, but it's also more defined more generally. Okay, so are there any questions about this part? I'm not seeing the chat place, so if there's something in the... Okay, I guess there's not. Okay, so now what do I mean by symplectic cluster manifolds? So this is not a standard name. And I'm only gonna talk about the dimension 2 case, but I think there are ways to generalize this, this type of story to higher dimensions. Okay, so the data that I want to start with is, so I have R2 with its standard oriented integral affine structure. And I claim that R2 can be equipped with a flat integral symplectic structure. And the symplectic structure is just given by, you take two vectors and you take the determinant of the matrix formed by those two vectors. This is also called cross product or wedge product. Okay, so this is this only depends on the oriented integral affine structure. Okay, not on a basis. Okay, now I want to consider a diagram of rational slope disjoint rays in R2. Okay, and I also want to equip each ray with a non-zero integer, though I'm gonna actually take this out later, but the story can accommodate for this extra data. And I want to call this an eigenray diagram, and the cross is nodes. Okay, so if I have an eigenray diagram, so it's something that looks like this with some numbers, then from that data I can obtain a topological manifold with an integral affine structure in the complement of the nodes. So the nodes are these crosses where the rays begin. Okay, and that's done by making a cut and then regluing the cuts using this linear transformation here. And this linear transformation, you've probably seen it as this matrix. It's an invariant, kind of more invariant way of writing the same thing. It's the same gluing, but you see that the data that's required to define this map is only this orientation data. It's only the symplectic form. Okay, and then this symplectic form, it also descends to the complement of the nodes in this glued space. And you can use this symplectic form to relate vectors with covectors. So that becomes handy. Okay, so now we have an integral affine manifold with some special monodromy. And we know that this kind of monodromy can be extended to, well, it's already extended almost here. So it's a topological, you can extend it even as a smooth manifold in this case, but it's higher dimensions, you won't be able to do it for sure. So maybe let's just say it's a topological manifold. And then this should, this data can be used to also define a symplectic manifold. Well, one way to describe what that is, I said how to interpret the Symington cuts as handle attachments, but there are other ways. You can just take the, you can look at the complement of the nodes, construct a symplectic manifold using the standard, you take T star of the base and then mod out by the lattice construction, and then you can show that the holes can be filled. That would be another way.
Umut, you have a question from Mohammed Abu Zaid.
Okay, I really would prefer if you just ask the question, because
it's okay. Is there some assumption of completeness with respect to the affine structure?
Oh, it's automatically complete in this case because it's R2, and I'm not saying I'm taking any base, right?
Yeah, I just don't know what it means, R2. I'm sorry, this is
just R2. I said everything that I said after this point is supposed to be precise.
Okay, so you take R2 with its affine structure? No, that's not what you, yes, you do. You take R2 with
affine structure, yes.
Okay, and then can you just repeat so that I understand?
So you just take some points on R2, and then you make some cuts, meaning that you take some rational slope disjoint rays. Okay, and then you cut along those and you reglue. This is the standard way of constructing. You can also think of it as a, you make a cut, and then you reglue something that looks like this, where the map here is identity, and the map here is the shear.
Thanks, I understand why you're not. I mean, anyway, thank you.
But does this answer your question?
Yes, it answers my question. I was worried about regions overlapping with each other, but that's not how you're describing it. You're describing in terms of rays and the monodromy.
Yes.
Yeah, okay, yes. Thanks.
No, I think it's a pain to try to actually construct integral affine manifolds. I don't know of any other general kind of way of constructing, even in this dimension. Okay, anyways. And if you were to allow the rays to intersect, there is a way to do that, but you have to kind of do it in order. You have to say which cut you're doing first and stuff like that. Okay, so now, if I have a symplectic manifold that's symplectomorphic to MR for some eigenray diagram, then I call it a symplectic cluster manifold. And one reason to call it a symplectic cluster manifold is because it admits some kind of mutation tree of inclusion from the cotangent bundle of the torus into it. Okay, and the way to see that is you have to do some kind of Vienna mutation, where you move some of the nodes far away enough along their eigenrays so that you can make a branch move to one of the nodes that you chose. And once you do that, then you obtain another eigenray description of the same manifold and another inclusion of T star T2 into the same manifold. Okay. Okay, so if I take MR above BR for some eigenray diagram, then there exists a K-analytic space YR over the same base with the property star above. And here I'm assuming that all the integers now are 1, and I also don't want to deal with parallel rays. So, I mean, I think the theorem should be true for including both of these guys, but I don't want to talk about it. Okay, so now some conjectures. So I conjecture that the other expectations are also satisfied. So this should be, I think, the correct mirror. So this is an analytic construction. So this is going to be constructed by gluing this kind of convex polygons. And I conjecture that this this symplectic manifold that I explained, this guy, should be a Looijenga interior with a hyperkahler rotated, hyperkahler rotated holomorphic symplectic structure. And you should be able to describe this U by using where the rays are and stuff. Okay, this conjecture. I also conjecture that this analytic mirror that I constructed is the analytification of some scheme over the Novikov field. And this scheme also should look like a Looijenga interior, and it should use the same combinatorial data. So one way to explain this kind of Looijenga interior, what it means is you take some kind of fan, and then you construct a toric variety over the Novikov field, and then you do some boundary blowups along the interiors of the, so non-toric boundary blowups in the interiors of the toric divisors, the components of the toric divisor. And there you have a whole kind of lambda star worth of points to choose, and kind of the moving of the ray in the transverse direction should be corresponding to kind of blowing up points with different valuations. Okay. Okay, and I think I know how to prove that there exists such a y such that the entire functions on y is the same as entire functions on yr. But for the, I don't know if it's true, like as if they're actually isomorphic as analytic spaces. Well, I mean, I shouldn't really say I proved this, but I think I know how one might prove it. Okay, so now how do we prove this theorem? So we use the strategy that I explained in the beginning. So first we use this locality theorem. So you take some, let's say, any compact set inside in the base of M, which contains just one singular point and doesn't intersect any of the other rays. Okay, not just the nodes, also the rays. Then you can define a new manifold by just erasing the rays that it doesn't, this compact set doesn't interact with, and define a new manifold that's called M tilde here, and let's call the corresponding set, compact set in the base P tilde. And then the locality theorem says that in this case, the whole SHM sheaf for compact subsets that lie inside this P that I fixed should be the same as the sheaf that I get here. So not just that there's an isomorphism of sheaves with the compatible with the restriction maps. Okay, so assuming, well, after this is true, then you see that it will suffice to analyze the two models that you see in the base. So the first model is just T star T2, which I will start calling M0 from now on. Fibering over B0, which is just R2. And also M1, this M1 has a bunch of C2 minus a conic with various symplectic structures that can be chosen, and it fibers over a base with just one singularity. Okay. So now, if I want to just show that YR exists as in the theorem, I just need to show the following things: that if P inside BI, so I is going to be 0 or 1, a convex rational polygon, and this I will actually require the singular point to be contained in the interior of the rational polygon. So rational means the sides are rational slope. Then I should know that this SH0 is an affinoid domain. Well, it gives an affinoid ring. And I should also know that the restriction maps are sub-affinoid maps. Okay, and this will follow from something more explicit, which is what I called local mirror symmetry above. So now let me introduce the mirrors, the local mirrors. So this the mirror of M0 is what I will call Y0 analytic. It's just the analytic torus, and it has the standard minus valuation map to B0. It's a tropicalization map. And I also have the mirror for the one singularity case, where I take the analytification of SH0, as I had said there. And this one, you know, these are analyzed by Concevic-Zoibelman first, I think, in this context at least. And this has a non-Archimedean analytic, if you want to add SYZ, but I don't want to say SYZ because I think this SYZ actually means something a little bit more specific in the literature than what I have in mind. That's why I don't want to use it, but that's what I mean. So it's okay. Anyways, let me not mumble anymore about that. So this should have also a continuous map which satisfies some properties to the base with one singularity. And this is explicitly analyzed and constructed by Concevic-Zoibelman. So now the theorem here is that if you look at the SH0 sheaf, and whenever I say sheaf, I have to be careful about which topology I'm considering. I'm being a little vague about that. So what the key point about these is that there is some kind of covering, let's say you can also consider all convex polygons. So there's an isomorphism between the sections over convex polygons, which are compatible with restriction maps. So this is just so being a sheaf is somehow not really important. It's something of pre-sheaf data. So topology is not that important for these. Well, it's important, but it's, you know. So what I'm showing is just about some compatibility with restriction maps. That's all there is to it when I say this is an isomorphism of sheaves. Okay, so on the A side, I have the SH0 sheaf, and on the B side, I just have the push forwards of the structure sheaves, analytic sheaf of analytic functions to the base under these maps. Okay, so this is supposed to be a theorem. So I want to just say a little bit about how wall crossing comes up in this framework, and I just want to explain that in the local model with one singularities. So as I tried to kind of explain, so inside this M1, there are two symplectic embeddings of T star T2. So one which misses kind of a portion of this eigenray, and another one which misses a portion of this eigenray on the left. Okay, so now, and I know that those embeddings can be so that on the upper half plane, they can both look like identity. Okay, on the lower half plane, they won't look like identity. But on the upper half plane, they can make them look like identity. Well, somehow, in the upper half plane, I mean any compact subset that's contained in the upper half plane. So let's take some compact subset, or let's say a polygon contained in the upper part of this monodrom invariant line. Then using the locality theorem, I get two isomorphisms with so these push forward sheaves, I call them Concevic-Zoibelman sheaf. Two isomorphisms with Concevic-Zoibelman sheaf over, so it's some kind of convergent functions over P. And these, because they're identified with the same guy, there is some isomorphism between them, and this is the wall crossing isomorphism. And the wall crossing isomorphism is not monomial, as we all know, and it's also, it can be shown that you can carefully analyze it so that this wall crossing is actually an entire automorphism of the pre-image of the upper half plane under the Concevic-Zoibelman fibration. And the map should be given by, it should fix one of the coordinates, and it should send, well, one of the generators of the coordinate ring, and it should send the other one to this T times 1 plus 1 over S. And there is a similar statement for the lower half plane, but something that's very confusing to me, and I was, really made me almost go crazy in the last days, is that there is monodromy also happening here. So I said that I can choose both of these inclusions to be to look like identity on the upper half plane. If you do that in the lower half plane, they won't look like identity. They'll look like they're symplectic lifts of a shear. And there is a wall crossing isomorphism that's happening for the lower half plane, and there's monodromy showing up. And it seems like the picture is completely symmetric between lower and upper half planes. but this seems a little hard. It doesn't seem like there's actually a symplectomorphism that switches the upper half plane with the lower half plane in the symplectic side. At least I couldn't find it. I don't know. So I always hoped that kind of the upper wall crossing transformation would like immediately determine the lower wall crossing transformation by some symmetry. And I thought I had an argument for a long time, but then I realized there's a gap in the argument. So I don't actually know if that's true, but I think it's maybe, so that way of computing the restriction maps was a little tricky. So I think the right way to compute the restriction maps is maybe the following. So I'd say I want to understand the restriction map from P prime to P. So the preimage of P prime to the preimage of P. And this is a picture in the base of M1, so B1. So supposedly I understand everything about this Viterbo invariance. So this the groups themselves are computed by Pascalev, and I think the restriction map can also be computed. But then what you want to do is you want to deduce the restriction map for the invariant SH0 of compact sets from this by certain completions. So what I claim is that if you consider P prime, which is some convex polygon that contains the origin, then the Viterbo symplectic cohomology, okay, with lambda 0, with Novikov field coefficients, should be dense inside this. Okay, and I'll try to give you some kind of reasoning why. And it should also, the same thing should be true for the model for the less singular point. And like this map should determine all these maps. Okay, and so the reason with this dense thing is, I think it should boil down to the following thing. So if you take a convex polygon in the local model, then every edge gives you a generator of SH0 Viterbo with respect to some integral some Liouville structure. And these are mirrored to functions on the mirror, basically by construction. Okay, but the location of the orbit of this of the orbit that gives rise to this generator is, let's say, along this edge. Okay, and this edge is also where the corresponding function takes its supremum. So using this, I think it's possible to prove that the norm induced on SH0 Viterbo under this kind of map is the same as the norm induced by the sup norm. Okay, so this somehow this going from kind of the Viterbo invariant to some invariant of the compact set that's kind of that contains the most singular point. So that is, you know, that whose boundary is a Liouville, who has a whose boundaries transverse to the Liouville flow and convex in also the integral affine sense. It should be the case that the invariant of the compact thing should be determined by some norm that's induced on the Viterbo invariant. And and there's also a norm that's induced on the mirror. So you know that the mirror of this guy and the mirror of this guy and the mirror of this map. And then you find the functions on the compact set by completion. You find the functions on this guy by completion. So everything should just follow from this being mirror to what it's mirrored to. Okay, does any questions about this? Did it make any sense at all? Okay. Well, so now, one way to kind of re-say what we constructed as the mirror here is, rather than gluing polygons, you can also glue this kind of larger regions. So there's an analytic space that lives over, the complement of these two yellow regions. with just one singularity contained. And you know, I can, for every singularity, I take an open set that contains the array of that singularity and just remove that. And then I can, instead of gluing polygons, I can glue these kind of sets, so this kind of analytic spaces. And the gluing happens along this analytic space, which is just a subset of the analytic torus. And the gluing should get something that has a continuous map over this. And so what I want to say is that if you just look at the global functions, removing these yellow guys shouldn't change the global functions. So instead of gluing these subsets with yellow regions removed, you can also glue just each of these guys are kind of analytifications of some affine space. And you can instead glue those affine spaces along an affine space and get some kind of algebraic mirror. And the functions over the analytification of that should be the functions over the original analytic space that we get by gluing these things. And therefore, so that should be this kind of Y that I claimed in one of the conjectures. And this is why I said that I think in the global functions level, this should be true. I think I have some remarks, but maybe I should stop here because I feel like I lost everyone already. So I don't want to lose any more people.
Okay, and you know, you do have 3 minutes. You're sure you don't want to take them?
Okay, I mean, I'll say something more, but yeah, it's a little strange. I'll say a little bit more. Okay, so now some remarks. So one remark about higher symplectic cohomology. So if you consider just the base of T star T2 and take this kind of non-convex domain, then, and if you look at SH1 of this non-convex domain, so in SH0, the SH0 of the non-convex domain is the same as the SH0 of the convex domain. It's like functions, and there's some kind of Hartog's lemma. You can't distinguish using functions something in this base from its convex hull. But if you look at SH1, you can actually, you see that they're not the same. And you can directly compute, because this boundary of this domain is star-shaped with respect to a radial structure. And you can just compute Viterbo symplectic cohomology with functions that are compatible with this boundary. And what you get in the end should be the usual Viterbo symplectic cohomology. So using that, you can determine kind of the differentials between the generators of this. So you can kind of make a global computation, but probably better is you should just use, you should just decompose this into 2 convex polygons like this, and just use the Mayer-Vietoris property that I had proved in my thesis. And you will see it there as well. So what I think the one way to interpret this in terms of mirror symmetry is that, so in the mirror, this H1 first theorem cohomology, I think it has 2 parts. It has the global kind of analytic one forms part, and there is also check cohomology of functions. This is kind of the spectrum, if like this Grothendieck spectral sequence. This is its kind of analytic version, if I hope exists. I haven't actually known, but I think it exists. And this one forms part is, I think, what's mirror to this convex hulls SH1, and this check cohomology part is, I think, this new, the new part of this SH1. So that, let me just say quickly, like, so there are these generators here in the same homology class, and they're kind of, the differential takes, differential has terms that take this guy and this guy to here, and the you know, the SH1 I know will have just one generator in that cohomology, and it will be the kernel of this map. Okay. But if you look at not just the same homology class, but multiples of this homology class here, and you'll see that these maps have increasing valuation. The energies of these Floer trajectories will get higher and higher. And therefore, you'll have something in the, so something in the first, at the chain level, you're gonna have some kind of infinite series where each truncation is in the image of the differential, but the whole thing is not in the image of the differential. So that will give this extra class on H1. Okay, I think now I'm actually out of time. And yeah, maybe I say, so for if MR was exact, then there's a lot of works about this. The main ones are, I think, Paul Hacking and Elsa Keating has a new paper, and also Schende, Troyman, Williams, there is some kind of sheaf theoretic version of this. And there are also algebraic geometry-based approaches by Gross, Siebert, Hacking, Keel, also Travis Mandel and Tony Yu. Yeah, and like this global functions on what I described is well understood if my mirror was over C. And this is a very kind of nice story where there's some kind of positive case, acyclic case, negative case, and you can see which case you are by looking at the integral affine geometry of the base and stuff. There's a very beautiful story, but I don't know how the story changes if you work over the Novikov field. And okay, since I started, I just finished. So it also seems like it can independently be checked that this analytification of the Looijenga interior over the Novikov field has a skeleton that indeed looks like BR. I asked this to two experts. One of them said it seemed true, and the other one had an argument for it. So it seemed like that might be. So this would be true if from what this would follow from what I said if my conjecture is true about Y. So the Y sub R being the analytification of the Looijenga interior. Okay, I stop. So now I went.
Okay, let's give Umut a hand. And if there are any questions for Umut, go ahead and either just call them out or put them in the text box.
I'll ask my question. So yes, at some point you mentioned something about wanting to build an algebraic structure. I mean, this you just were talking about algebraic structure on this mirror space. So naively, but it seems that you already talked about some of the pieces that you would need for this algebraic structure.
Yeah.
So
I did. I did. This analytic mirror basically comes from, rather than covering your manifold by polygons, you cover your manifold by these large open sets that I described.
Is it clear that you get a sheaf with respect to that topology? Yeah, so that was my question. Indeed, I asked, oh, you can't see it anymore. Okay, so this happens. I think I just have to stop sharing and reshare for 1 second. Yeah, so I think for R invariance, I think it's true. I didn't write, that's the part where I might need to take an inverse limit at the chain level. But I claim that indeed, if you have open sets, covered by open sets, and each of those open sets admit an exhaustion such that the members, each ith level of that exhaustion satisfy the sheaf property or descent property, then the open sets should also satisfy the descent property. Yeah, but this invariant that you would get for the open set would not be the ring of algebraic functions. No, it would be the it would be the entire functions on the analytification of that. But all the maps that are in this diagram would be also analytifications of algebraic maps. So I'm not claiming anything about the algebraic mirror. All I'm saying that my analytic space is an analytification. Like I don't have a way of making sense of the algebraic mirror. Like I don't know the A side of the algebraic mirror. That's just a way for me to describe what I get in a more concrete way. But it seems that you're saying that a posteriori, you would actually know that there are that you have restriction functions, restriction maps of rings of algebraic functions.
Yeah, but that's not really, well, in order to really make sense of that, you would need to define Viterbo type global invariants, I think. Like, yes, they're that, but they don't, the fact that they're that doesn't really mean anything in Symplectic. Like the place where they come from, like I say that I have a map of analytic spaces, that's an analytification of an algebraic map. It's true as a statement, but the algebraic map doesn't really correspond to something in the symplectic side. So I don't know what statement to make about the algebraic space.
Didn't you say that you basically proved that that restriction map is the Viterbo restriction of the inclusion of one Liouville subdomain inside another?
But that's just the local case.
Okay, I'll think
the global manifold is not a Liouville manifold.
No, I understand that. Yes, I understand, which is why it's interesting.
Yeah.
Okay.
Yeah, I think so. But I did want to ask if, in the exact case, to me, it seems like SH0 Viterbo should satisfy some kind of sheaf property with respect to that open covering. It seems like that, at least. I don't know. But I mean, is this possible, or I don't know. I wanted to ask this.
Yeah, I don't know another way of proving it other than,
because I mean there's this co-sheaf property maybe, and yeah, this integrability should come up somewhere in this proof. So I mean the way I get this the analytic version of this sheaf property is by approximating and then using that compact sets and approximations are lifted from the base of an integral affine structure, the Lagrangian fibration. And the sheaf property for open sets comes from some kind of by construction almost. Yeah, I don't know how else one could prove it.
Umut, I wanted to ask, in your remark 3 just above, you said that the story's been worked out in detail over C. Could you share a reference or two for that story over C?
Yeah, I think I can even show it. It's right next to me. I think this, I mean, it has precursors in so this is the one. Okay, so it's called Classification of Rank 2 Cluster Varieties by Travis Mandel, but he is building on a work of Gross, Hack, and Kiel. So yeah, should I write it?
I think that's okay. Yeah.
Meaning yes or no?
I think you don't need to write it down. Yeah, but thank you.
Yeah.
Marco, you can go ahead. Okay. Okay, so Marco asks a question in chat. Maybe I'll read it for everyone. Thinking about compactifying M with some divisor D, is there a good notion of sheaf of L infinity algebras? And if so, should relative symplectic homology satisfy it?
So I don't understand the first part of the, why are we thinking about compactifying? Do you mean deformed SH maybe? So are you saying that we look at open sets inside the compactified space? Okay, I don't, yeah. Anyways, so the sheaf property is general. It's a complement of a divisor, yes. So the sheaf property just requires you to have an integral affine, a Lagrangian fibration, sorry. A Lagrangian fibration, and there is going to be a sheaf property in the base of that. So about L infinity algebras, so I think when you say a sheaf of algebras, for example, what you mean is you have sections are algebras and restriction maps are algebra maps. And the sheaf property itself is is not about the algebra structure. So in that, if I said that correctly, then at least, yeah, I would expect this is true. Yeah, I think all restriction maps should be L infinity, should have L infinity structures. Sorry, it should respect L infinity structures. And that should be a sheaf of infinity algebras, I think. Yeah, I don't know. It's a little hard to communicate with that.
Any more questions for Umut? Okay, then let's give him another hand. Great, then I'm going to paste links right now into the chat for our usual two things, suggestions for speakers, and also any tips or comments about the logistical setup for the seminar. And so we'll end the questions there, and then if anyone wants to stay on, I think Umut is happy to chat with anyone who wants to talk a bit more in detail or in private.